What is OrthoFlow and why should I use it in my deep learning workflow? I answer this question in detail on my GitHub repository soprenum.de OrthoFlow, but it becomes much clearer when I use an example. And so, welcome to the video on OrthoFlow, CIFAR10 and DenseNN. The video DenseNN, CIFAR10 and SVD demonstrates that Singular Value Decomposition, SVD, can reduce the number of network training parameters from approximately 2.5 million to approximately 286,000 parameters. SVD is commonly used method in image processing because the loss of quality due information loss is kept to a minimum. This video demonstrates that SVD is not particularly efficient. That changes with OrthoFlow, as it implements a high-performance SVD. The diagram shows the integration of OrthoFlow into an r-DenseNN workflow for training a deep learning model. However, OrthoFlow not only provides a high-performance SVD, but also data validation and scaling method. The SVD matrix is output as a projection matrix in CIFAR format for direct use with DenseNN and in binary format for custom use. This diagram provides an overview of the OrthoFlow workflow. You can read all about this and more on the GitHub project page. And I think it's time for an example of an OrthoFlow R workflow. The R script CIFAR10 OrthoFlow describes how to use OrthoFlow followed by deep learning architecture training using DenseNN. It should be noted here that OrthoFlow can, of course, be used independently of DenseNN. The script can be downloaded from the GitHub repository Soprenum OrthoFlow R scripts. This section loads the necessary R package. However, the reticulate package is only required if you intend to load the binary NPy files. This script does not do that, so we will not cover it here. I'm running this section of the script and load the CIFAR10 training and test dataset. The process for preparing the dataset is described in the video DenseNN, CIFAR10 and SVD, so we will not cover it here. But now comes a crucial step. SVD should be performed on the training and test dataset using the same parameters and the same dimension reduction factor. For this reason, both datasets are combined into a single dataset and later separated again. The entire dataset is saved as a CSV file. The execution of the script portion takes some time due to loading and saving and of course has nothing to do with the SVD performance. Now I will finally get to OrthoFlow SVD. OrthoFlow is called in the same way as DenseNN and variables are provided with the necessary parameters here for better readability. I run the OrthoFlow SVD and receive an SVD report shortly afterwards. You might be thinking, that the SVD wasn't that fast, but I would like to direct you to the SVD log. You are probably familiar with the SVD in principle, so I would just like to point out here that the SVD was calculated using the Intel Math kernel library and set a threshold value of 99% for the explained variance was used to determine the reduction factor K. Let's now move on the OrthoFlow output. All output files are stored in the OrthoFlow output directory. Here you can see the important output files, including dense input CSV, which can be used directly as an input file for DenseNN, as well as the binary NPy files that will be used later. The contents of the SVD projection file correspond to the contents of the dense input file. The scree plot provides a graphical overview of the reduction factor K. Based on the threshold value, the number of columns was reduced from 3072 to 232. This corresponds to the number of input nodes for the deep learning architecture to be trained. The JSON files are used internally by OrthoFlow, but you are welcome to view them. If you have forgotten the dimension of the reduced data matrix, you can find that information in the SVD JSON file here. However, please do not modify them under any circumstances. A log file is generated for each OrthoFlow run and saved in the logs directory. It shows the degree of parallelization, which SVD variant was used, and what the threshold value was. Next, the internal structure of the execution pipeline in OrthoFlow is listed, followed by the first major time-consuming step, loading the data file. And here, the time required for the actual SVD can be calculated as the difference between the two steps. And for this dimension of the matrix, that's actually not bad at all. Now the entire dimension-reduced data matrix must be split back into a training and test dataset, which is done in this section of the script. The split has been completed, and now the deep learning architecture can be trained using by dense_NN with the parameters shown here. The number of input nodes is, of course, determined by the reduction factor calculated via OrthoFlow SVD. I started the training, and the console displays the usual dense_NN information. After 200 epochs and about 200 seconds, the training using this training data is completed. We know that a dense network architecture isn't the ideal structure, so I'm quite satisfied with this data. As shown in the previous dense_NN videos, the training progress can also be visualized using the R script display training progress. However, since that is an actual different topic, I don't want to go into it any further here. However, to run out the example, I will also run the test on the OrthoFlow processed data, which will result in the confusion matrix shown here. And that brings me to the end of the video OrthoFlow, CIFAR10 and dense_NN. Basically, the R script consists of calls of the C++ program OrthoFlow and dense_NN. The rest is just supplementary code for constructing the sample dataset and providing network visualization options. So it's all very streamlined and, as I said, highly performant. The R script also demonstrates how easily OrthoFlow can be integrated into a training workflow. Of course, OrthoFlow and dense_NN can be integrated into a Python workflow just as easily and efficiently. I hope you find OrthoFlow and dense_NN useful for your project, and I would appreciate your feedback. See you soon.